Okay, so today we're really diving deep, huh? We're taking a look at how we fight back against those tiny but mighty viral infections.
Uh-huh.
I've got some pretty in-depth notes here from, let me see, pharmaceutical biotechnology, specifically Unit 3.
All right.
But we don't want to just define antiviral drugs, right? We
Right.
want to get into how they actually work, the mechanisms, the strategies.
Absolutely.
Now, everyone's heard of antibiotics, right? For tackling bacteria.
Yeah.
Antivirals, whole different game.
Totally different. You see, antibiotics, they kind of work like a general disinfectant, you know?
Okay.
But antiviral drugs, they're way more targeted. They're designed to zero in on the very specific ways that viruses make more of themselves inside our cells.
Mm-hmm.
Like think of it as a key that only fits a specific lock, viral lock.
Okay, I like that key and lock idea. So in our notes here, we've got two antiviral drugs that are highlighted, amantadine, and then there's azithromycin, better known as AZT, I think.
AZT.
These two seem like they give us a pretty good, like a good contrast in how we can approach this.
Yeah, and what's really interesting here is that they target different stages of a virus's life cycle. So, you can think of a virus as this tiny invader with a whole plan, right?
Uh-huh.
It needs to get inside a cell first, that's entry.
Right.
Then it has to copy its genetic material, so that's replication.
Okay.
Those copies, they get put together into new viruses, assembly,
Mm.
and finally, all these new viruses, they burst out to go infect even more cells, and that's release.
So that whole sequence, entry, replication, assembly, and release, amantadine and AZT, they kind of step in at different points in that timeline, right?
Exactly.
Now, I'm looking at the notes here, and it says that amantadine, it mainly messes with the virus's ability to even get into the cell in the first place.
Right, so it's like blocking the door before the invader can even get in.
Okay, so amantadine is the bouncer at the club. Got it.
Yep.
What about AZT?
AZT, it works a bit later down the line.
Oh.
So think of viruses like HIV, right? They use RNA as their genetic material. And to make more of themselves, they need to turn that RNA into DNA.
Okay.
There's this enzyme called reverse transcriptase that helps them do that.
Right.
AZT basically acts like a faulty building block.
Oh, okay.
So when the virus tries to use that reverse transcriptase to build new DNA, it grabs AZT thinking it's a regular component, but it throws a wrench in the whole process.
So it's like sabotaging the copying process from the inside.
Exactly, yeah.
Yeah.
So you've got amantadine blocking the entry, and then you have AZT disrupting the replication.
It's really amazing how, like, to develop these treatments, you have to really understand each step of the virus's little plan.
Right, and that's what's so cool about this. Once you figure out where the virus is vulnerable, then you can design a drug to just target those weak points specifically.
I guess that's what makes antiviral drug development so much different from antibiotics. It's not just about finding something that kills the virus outright.
Yeah, it's more like it's like figuring out how to disrupt this intricate dance between the virus and our own cells and finding that one move to just throw the whole thing off.
No, if we're thinking about this, like, from the listener's perspective,
Sure.
the takeaway here is that antiviral drugs, they're like specialized tools, right?
Yeah.
They're designed to stop viruses from multiplying within our cells, and unlike those broad-spectrum antibiotics that just go after bacteria, antivirals need to be way more precise.
Probably they got to be specific to how that virus works.
And as we've been talking about with amantadine and AZT as our examples, these drugs can target such different stages of the viral life cycle, like we were saying, from keeping it out of the cell in the first place to actually blocking the copying of its genetic material.
Right.
So this kind of leaves us with a thought, to ponder. Thinking about how complex these viral life cycles are and the different strategies that drugs like amantadine and AZT use, are there other points in the viral infection process that we could target?
Yeah, I mean, it makes you wonder.
Could we develop drugs that are even better at, disrupting the assembly phase or even the release phase?
Definitely something to think about.
It's a pretty fascinating area to consider, especially with all these new and constantly evolving viral threats that are out there.
Oh,